Hello, this is mathjazz from Almost Cool. This is an exponential review video. We'll be talking about graphing various exponential functions, and that's really it. So first, we're going to make a t-table here. We have values of x on the top row and values of 2 to the x on the bottom row. We've graphed these points 1, 2, 2, 4, 3, 8, and so on this chart. And this is going to be how we're going to start building up the outline of our graph of the function of 2 to the x. Hello, this is mathjazz from Almost Cool. Today we are reviewing exponents. So today we're entirely talking about how to graph exponential functions. So our first goal will be to just collect a bunch of points that are on the curve 2 to the x. 2 to the x is the curve that we're going to focus on first. And then we'll go to some other bases and we'll end with graphing e to the x. But for now, 2 to the x is good. So we're going to let x be 1, 2, 3, and 4. We know how exponents are defined to be repeated multiplication. So 2 to the 1 is 2 times itself one time, which is 2. 2 to the 2 is 2 times 2. 2 to the 3 is 2 times 2 times 2. And so we can easily come up with the values that we should have for 2 to the x for positive integer values of x. And I've collected 4 of those here and graphed them on this chart. So the next thing we need to do is we need to extend our definition of 2 to the x onto the negative integers. This isn't so bad either. We think of if we're going to add 1 to the power, we multiply by 2 again. So going from 2 to the 1 to 2 to the 2, we're just multiplying what we had, the value 2, by 2 to go up. This gives us the natural way to define our negative exponents by saying, well, instead of going from 1 to 2, going from 1 to 0, we should be dividing 2 to the 1 by 2 and getting 1. This is why any number raised to the 0 power is 1, with the exception of 0, but we won't worry about 0 or negative bases in this video. So going from 2 to the 1 to 2 to the 0, it goes from 2 to 1. And if we keep going, we keep dividing by 2. 2 to the negative 1 becomes 1/2. And then we go to a fourth and an eighth and so on. And now we have a nice definition for all of our values of 2 to the x on all integers, both positive and negative. And now we come to fractional powers. So we want to have a nice consistent definition for what it means to raise a number to a fraction. And so the way that we're going to do that is, I'll just borrow some space here. So 2 to the, let's say, 1/2 power should be a number so that if we were to square this, we should get back 2. So this leads us to think that fractional exponents should be just roots. So a 1/2 power, that's 1 over 2, we should have a square root for our 1/2 power. 2 to the 1/2 is the same as the square root of 2. 2 to the 1/3 would therefore be the third root of 2. And we find this nice relationship between powers and roots. That is, if you're raising some number to a power, that is the same as raising or taking the reciprocal of that power, root of your base. So 2 to the a over b is the same as the b over eighth root of a, or 2. Yes, 2. 2 to the a over b is the same as the b over eighth root of 2. So I'll delete this. So that gives us a nice description of how to handle fractions. And so I've listed all of the integers between -5 and 4 and all of the multiples of a half. And we've had this nice plot starting to show up. We actually have a definition for every fractional value of x. So for every fraction, for every rational number, we can now find a value. And here we go from having a definition on all fractions, on all rational numbers, to a definition on all real numbers, including the irrational ones, by saying, well, we want our function to be continuous. And so if you haven't talked about continuity yet, if you haven't learned about that, that's fine. But for those of you that have talked about continuity before, have learned about continuity before, the way we uh, define the value of 2 to the x when x is irrational is we pick the value that makes 2 to the x a continuous function. Anyway, so we can start connecting all these points in a way that makes a continuous function, and we get something that looks like the blue curve in this graph. So let's go back. We're just connecting these dots. We get this beautiful blue curve here. We will notice that as x goes to negative infinity, we have a horizontal asymptote at 0. And as x goes to positive infinity, our function will go up to infinity. So this is a nice function that has a one-sided horizontal asymptote. This typically doesn't happen, well, this doesn't happen at all in rational functions, but this is a nice equation, a nice expression that has no strange step functions, no weirdness about it, no piecewiseness about it, but still has a one-sided horizontal asymptote, which I think is pretty cool. Now, this yellow line that I've drawn, this represents the tangent line to 2 to the x at the point 0, 1. And if you haven't talked about derivatives and tangent lines, that's fine. You can come back to this video after learning about derivatives and tangent lines, and this will make more sense. But this line here has a slope of the natural log of 2. And if you haven't learned about natural logs, that's also fine. You can watch the video on natural logs and then come back and watch this. But this is something that we're going to build up to. Is this slope here just happens to be a little bit less than 1. If we did the same procedure to 3 to the x, building up powers of 3 on integers and on rational numbers, and then doing what's called a continuous completion and connecting all of the dots for a function, we get this curve here. Now, the axes are a little bit different scale between the 2 to the x graph and the 3 to the x graph, but the tangent line at the point 0, 1 turns out to have a slope a little bit bigger than 1. This is a slope of the natural log of 3. And 4 to the x, if we did the same thing, we'd have the natural log of 4 as the slope of our tangent line. In general, we can take any positive number, rational or irrational, and make it the base of an exponential function. For single variable calculus, for real valued calculus, we don't look at non-positive bases. All of our bases are positive numbers. We can take fractional bases like a half. Notice that 1/2 is equal to 2 to the negative 1, so that means that 1/2 to the x is equal to 2 to the negative x. So to get a graph of y equals 1/2 to the x, that's the same graph as y equals 2 to the negative x. And notice it's just a reflection across the y-axis, which is exactly what we would expect if we were to take the graph 2 to the x and flip it over the x-axis. That would just be changing the sign on the x. Here's a chart of all 4 of these exponential functions placed on a graph together. The blue curve is base 2. To me that looks yellowish, is base 3, and the green one is base 4. and the orange one is base 1/2. If we zoom in on these, zooming in close enough, the graph of the equation or the graph of the function is going to look like the graph of the tangent line. That's why we can use tangent lines to approximate curves when we have a small enough region that we're looking at. So here are the graphs of the functions. It's, again, equivalent to looking at the graphs of the tangent lines at this scale. And we notice that the blue curve, or 2 to the x, and the yellow curve, or 3 to the x, right in between the two of these, we should have a graph of the line x plus 1. Here's a graph of that. This also looks blue to me, but it might be purplish. I'm unsure. But anyway, this new line right between the 2 to the x curve and the 3 to the x curve is the line y equals x plus 1. And this would be a really nice base to know. If we knew what base of an exponential function would give us x plus 1 as a tangent line, that seems like a really natural base to use for an exponential function. As again, 2 gives us this weird irrational slope of natural log of 2. Using a base 3 gives us an irrational slope of slope log 3. What we really want is to have a base where that base has a tangent line with slope 1. And we define the number e to be that number. Here's a graph of e to the x. E is defined as the number where if we have an exponential function with it as the base, then the tangent line when x is 0 has a slope of 1. There are other ways you can define e to the x. They all come out to be equivalent to each other, but that's, I think, the most common definition of e. So here's a graph of e with its tangent line. E to the x is the blue curve, and the tangent line is the yellow curve. And here's a manipulatable graph. This lets us see how various coefficients and constants affect the graph of e to the x. So notice that a will produce horizontal stretching and compressing. If a is negative, then the graph reflects across the x-axis. B shifts the graph left and right. Wait. Oh wait, A should be left at 1, not at 0. There we go. Shifts the graph left and right. That was very confusing for a moment. Because a shift on the inside of a function, adding a number to the inside of a function produces a horizontal shift. This function behaves just like every other function when it comes to horizontal, vertical translations, or compressions, or reflections. C is a constant on the outside of the function, so it will produce vertical stretching. And if it goes negative, then we have a vertical reflection. And D is a constant on the outside of the e to the x function, so it produces vertical translations. They're kind of fun to watch. Let's turn on all of the automatic playbacks for a moment and just watch the graph change. It's really cool. Well, anyway, this was our review of exponential functions. Thanks for watching. Oh, I hope that you have a great day. Goodbye.